In 1998, astronomers found that the expansion of the universe was not slowing down due to gravitational attraction as expected, but something astonishing was happening. The expansion was actually getting faster and faster. It was accelerating. Something must be powering this acceleration of the universe. But since we don't know the source of this energy, it is called dark energy. It's one of the most mysterious aspects of nature and appears to be the most dominant energy form in the universe, making up more than 2/3 or 68.5% of all the energy in it. The rest is regular matter that we can see and dark matter that we can't see. Now, dark energy should not be confused with dark matter. They are both labeled dark because we don't know what they are. But these are two different things. Dark matter does not absorb, reflect, or emit any light, so it is undetected. It is inferred to exist only because of its gravitational effect on galaxies and galaxy clusters. We know that it's not just energy, but matter in the form of particles, or at least that's what the best theories propose. Dark energy, on the other hand, appears to be some kind of energy that is powering the accelerating expansion of the universe. But wait, is it possible that dark energy could also be due to some kind of particle? And could this particle be related to the Higgs boson and dark matter? That fascinating story is coming up right now. Before we get started, I want to give a big shout out to Magellan TV, without whom videos like this could not have been made. One fascinating documentary that made me think of the topic of this video is called The Mystery of Dark Matter. They use animations to show how dark matter appears to be everywhere in the cosmos and include interviews of astrophysicists and cosmologists to help you understand what it could be. But this is only one of thousands of great documentaries on Magellan TV, a new kind of documentary service created by the filmmakers who bring you the highest quality content. Featured topics include science, history, travel, and technology. You can enjoy these documentaries with a free 1-month trial that Magellan is offering right now to Arvin Ash viewers. All you have to do is click the link in the description. Not only will you enjoy great content, but you'll be supporting this channel as well. So I really thank you for that. Now, back to the show. The story of dark energy goes back to none other than Albert Einstein, trying to solve his new field equations of general relativity, which he presented in 1915. His solution, published in 1917, required a certain addition to the field equation, the infamous cosmological constant lambda. The reason he added this term is because in those days it was reasonable to think that the universe was static and finite. It was thought that the universe had a specific size, which did not change. It was the solution for a static universe. Without this lambda term, the equations modeled a dynamic universe, which was either expanding or collapsing, but not staying static. The constant would cancel out any expansion or collapse and show that the universe was static. But in the 1920s, American astronomer Edwin Hubble showed that most galaxies were moving away from our own Milky Way galaxy, and the farther away they were, the faster they were receding. The universe had to be expanding. Although Einstein initially did not believe the universe could be expanding, he eventually admitted defeat in 1931 and said that adding lambda to his equation was his, quote, greatest blunder, unquote. But it turns out that even when Einstein thought he was wrong, he was more or less right about lambda. In an astonishing turn of events, due to the discovery of the accelerating universe, it turned out that inserting lambda back into Einstein's equation could account for the accelerating expansion of the universe. The positive value of lambda just means that it works as a repulsive force, a bit like anti-gravity. We can illustrate the force of such a potential energy with gravity and the cosmological constant like this, where F is the overall force, G is Newton's gravitational constant, M is the mass of the object, lambda is the cosmological constant, and R can be understood as the distance from another object. In this form, the negative sign of the gravitational potential means attraction, and the plus sign on the cosmological term means repulsion. If the first term is larger, gravity dominates and objects would tend to clump up. If the second term is larger, repulsion would dominate and objects would tend to fly apart. It's important to note that for gravity, the potential gets weaker and weaker at longer and longer distances because the R term is in the denominator and it's squared. But note that for the lambda expansion portion, the R term is in the numerator and is not squared. This means that things nearby will be attracted to each other to form solar systems and galaxies. But over very large distances, the gravitational term rapidly diminishes due to R squared getting larger. And because the R is in the numerator for the cosmological constant term, expansion forces dominate and things repel at large distances. So what we see in the universe is that on smaller distance scales, such as, for example, within our solar system or even within our Milky Way galaxy, things continue to stick together. But stretched out over very large scales, millions and billions of light years, galaxies in general move away from each other. This is because the cosmological constant dominates at these scales. Today, the most widely accepted model in cosmology has this cosmological constant. But unlike the days of Einstein, where he put it in to make the universe static, we now put it in to make it expand at an accelerated rate. And today, the cosmological constant represents dark energy. So this constant is thus a possible candidate for dark energy. But this is just a number, a mathematical solution to our observations. What does it actually mean? Physically, it can be thought of as the energy of empty space, also known as the vacuum energy. Quantum mechanics shows that empty space contains energy. Although the cosmological constant solution is a simple solution to the problem, it's something we have to add in by hand. We calculate what the number needs to be based on the observed rate of expansion of the universe and then insert it into Einstein's equation so that it fits with our data. This hand-calculated value of lambda is about 2 × 10⁻35 inverse seconds squared. But it's important to note that this value is nowhere near the theoretical prediction of what the energy of the vacuum should be, based on the ground state energy of all the quantum fields. The theoretical value is about 10 to the 120 times larger. This has been called the worst prediction in the history of physics. So when it comes to lambda, something is not adding up between our observations and our theories. Nevertheless, the cosmological constant is the simplest solution to dark energy and works well as long as its value is constant. But is it really constant? Some of the newest and most advanced observations seem to indicate that it might not be a constant. If that's true, then this would lead to a solution with dynamical dark energy, or a theory where dark energy changes over time and space. If this were the case, it could be evidence in favor of viewing dark energy as a field, not as a constant of nature. This is because fields can take on different values in space and time, rather than staying constant. We could then imagine dark energy as a scalar field with some potential. This, in some ways, is like how the Higgs field works. The Higgs field is also a scalar field, and it has a non-zero potential. The dark energy field, on the other hand, may or may not have a non-zero potential. In the context of dark energy, such a field is more commonly known as a quintessence field. Now, anytime you have fields, you have particles. This is because excess energy in a quantum field, or excitation in the field, is what we observe as particles. So this would point to a particle solution for dark energy. These particles must then interact with matter particles of the Standard Model to act as a kind of anti-gravity force. This force would be like electromagnetism, but instead of causing repulsion and attraction with charged particles, it would only impart repulsion, and to all matter particles. This is called the quintessence model of dark energy. The term quintessence comes from ancient Greeks who believed that the universe was made of 5 elements: earth, air, water, fire, and a 5th element that all objects in the heavens were made of. Latin scholars later named this 5th element quintessence. Today, this term in physics is used to describe the hypothetical dark energy field. Now, the question we have to ask is, if such a quintessence field exists and its effects are so profound, why didn't we detect it? Well, it could be that the interaction between the Standard Model particles and dark energy field is so weak that we simply don't have good experiments or sensitive enough instruments to detect it. But it could also be that such a field does not exist. A particle solution like quintessence would likely affect many things because particles interact with the stuff of the universe. This has an impact. Those interactions should be detectable. Furthermore, depending on the nature of the field, it could possibly also be part of a solution explaining dark matter, in addition to dark energy. Since quintessence fields give rise to particles, such a solution may show a connection between the dark matter particles as well as dark energy. But we should still remember that theoretical dark matter particles have a different effect in the universe than theoretical quintessence particles. There are stark differences, such as dark matter appears to be present in clumps in the universe, whereas dark energy is smoothly distributed. As the universe expands, dark matter gets less dense, but the density of dark energy stays constant. Dark matter has an attractive effect to slow the expansion of the universe, whereas dark energy has a repulsive effect, accelerating the expansion of the universe. Having said that, it is possible that both particles are part of the same quantum field theory, connected perhaps at a higher level in as yet an undiscovered grand unified theory. If they are related, the relationship is hidden from our current understanding of the universe and is probably quite subtle. An interesting consequence of a dynamical dark energy solution like quintessence is that the repulsion could get stronger and stronger as the universe expands, meaning the universe would have a runaway acceleration. It would become so strong that it would eventually rip everything apart. First, all galaxies would move away from each other so that it would appear as if our Milky Way galaxy is the only galaxy in the universe, because we would not be able to see the light of any other galaxy. Then our galaxy would be ripped apart. All the stars, including our sun, would then be ripped apart. Eventually, the repulsion would become so strong that the cells and later molecules, then atoms, would be ripped apart until everything in the universe becomes nothing but fundamental particles. This is called the Big Rip. And of course, in such a universe, no life could likely exist. Finally, space-time itself would rip apart, and all distances in the universe will be infinite. This might be scary, but we can't rule out the possibility. Fortunately for us, this would happen hundreds of billions of years in the future, so no need to lose sleep over it tonight. And if you have a question about this or any other subject in my prior videos, please leave them in the comment section. I'll do my best to answer it. And if you enjoy my videos, please subscribe. It costs you nothing, and it really helps us out. I'll see you in the next video, my friend.